Hi everyone, welcome back to the channel. I'm Crispy. It's been a while, but I've been busy. Let me show you what I've been up to. Now, I know in the last video I said that this video was going to be us placing down components on the board and routing some high-speed signal traces. I lied, and I'm sorry. I got a little carried away, and this is where the board is at right now. So I think the best thing to do right now is to just give a general overview and just kind of talk about what's happening here, because honestly, this is just a ton of colors and it's even confusing to me. So let's get started. So we're going to start just above the compute module right here. This is the fan connector that the FPGA controls so that it can control a 4-pin fan. Next to that, we have the camera connectors, which connect to the compute module 4. To the right of that, we actually have a I2C interface for the compute module. Now, I wanted to include this in a header because it's actually used for the camera. This just gives the compute module 2 pins that it can control that aren't tied to the FPGA at all, which should be helpful if I'm having issues with the compute module working, just seeing if it's actually turning GPIO pins on and off. So an added bonus to this is that since this is the I2C interface, you can just use 2 pins and you can hook up, I think it's 128 sensors max just on these 2 pins, and all that data is just sent to the compute module itself. So that's pretty nice. Below that, we have the PCIe Gen 2 1X connector. Below that, we have the USB hub and the USB 2.0 ports. So how this works is if we zoom in, this is the compute module right here, what I've highlighted. And the compute module has a single USB 2.0 output, which is actually what I have highlighted here. So this single output goes to the USB hub controller, and then this manages the single upstream port and makes 2 downstream ports, which all that means is that the USB signal from the compute module goes into this integrated circuit, and then the integrated circuit makes 2 downstream ports, 2 USB ports that you can plug a mouse and keyboard into, your thumb drive, a USB to Wi-Fi adapter, whatever you need to. So it's nice to be able to take one and convert it into 2 because one USB port isn't that useful. Below that, we have the Pi Ethernet. Now, the compute module 4 is really cool compared to the compute module 3 because they've actually added on the extra integrated circuit and all the passive components that you need to implement Ethernet compared to the compute module 3. So to implement Ethernet on the compute module 4, all you need to do is get an Ethernet jack and then connect the high-speed traces to it, which are a bit difficult to see, but they actually originate over here and then they come across to there. Below that, we have the HDMI connector. This one was a super easy routing because we literally just went from left to right here. So it's awesome. And in the bottom right corner, we have the SD card for the compute module. So this is where you put the SD card that you want the compute module to boot off of. Below that, we have activity and power LEDs. The activity LED will flash when the compute module is actively doing something, which is great for debugging to see if it's actually working or not. And power just lets you know if the compute module is actually outputting power. Because another great feature of the compute module 4 versus the compute module 3 is that you give the compute module 4 a single 5-volt supply, and then it will make the 3.3 volt and 1.8 volts that it needs. Versus the compute module 3, where you had to make those 1.8 volt and 3.3 volt lines yourself on your board and then feed that into the compute module. Next to that, we had the GPIO header. Now this is the main GPIO header for the FPGA. And basically how this is set up is everything to the right of my cursor right now, all these pins, are just general purpose GPIO pins. But to the left of it, these are also GPIO pins, but they can also serve as analog to digital converters. Below that, we have some user input buttons and 16 LEDs. Now, I love LEDs on FPGA development boards. It's just so nice and so quick and easy to get what your output is, up to a 16-bit output with just a few lines of Verilog code, compared to having to figure out like, okay, I got to set up the SPI interface between the FPGA and my compute module in order to get what this 16-bit value is. Nope, don't need to worry about that. Just send it to LEDs and you can visually look at it. Love them. Love LEDs. Next to that, we have the ADP 5054. If you remember, this is actually the first power IC that we set up. Above that, these are actually the power inductors. So the ADP5054 has the 1 volt output, 3.3 volt, and 5 volt output, and you need to have some pretty beefy inductors with those. So they do take up a lot of space, but they seem to fit pretty nicely. Next to that, we have the power header. Now I love to have power headers on my board because it's just so easy to grab whatever voltage I need and bring it out to a breadboard, or it's even easier to make a really simple PCB that plugs into that and then utilizes those power connections. Above that, we have the main power input for the board. This is a 12 volt input. And above all that, we have the FPGA's Ethernet interface. So I talked about this briefly when we were actually drawing out the schematic for the Ethernet PHY chip. How it works is the FPGA acts as the MAC, or the media access controller. And then you just need to connect the FPGA to the PHY, which is the physical layer, and then the PHY is connected to the Ethernet jack. Above that, we have all the configuration, and really just these are the pins that are in the center of the FPGA. Now, this 6-pin JTAG header is actually not going to be fitted on the final board. I'm including it merely as a convenience for people that want to program or debug their FPGA using existing Xilinx tools. But for the average maker that just wants to use FPGAs in projects, they probably won't need to use it. To the left of that, we have the Done LED. This is the LED that will illuminate once the FPGA is done configuring. And to the left of that, we have the dedicated analog to digital converter. This is using an MCX connector, which is great because MCX connectors have adapters to convert to BNC connectors, which oscilloscope probes use the BNC connector. So it's really easy to attach an oscilloscope probe to the FPGA, which I plan to do for a future project on this channel where we make our own oscilloscope. To the left of that, we have the auxiliary I/O bank. This one is actually laid out the exact same as the other GPIO bank, where these pins here are just straight up general purpose GPIO pins. But the pins above are, once again, either GPIO pins or they're analog to digital converters. So in total, you actually have 17 analog to digital converters on this board, which I just love. And to the right, we have this IC, which is actually the clock. You can think about this like the heartbeat of the FPGA. The clock signal is what moves everything forward in the FPGA. And above that, we have the FPGA, the star of the show. And above the FPGA, we have the PCIe Gen 2 4X connector. And finally, we've come full circle to the DDR3 SDRAM. Now you may be asking yourself two questions. First one, there's DDR3 SDRAM on the board? Yes. I actually made a Reddit post where I just kind of explained this project and what I was doing. And the best feedback I got was that the SRAM that I originally had on the board didn't really make a ton of sense, and it would be better just to implement DDR3 RAM. The second thing you're thinking is, wow, Crispy, that looks incomplete. And you are correct. I have not finished this yet because I severely underestimated DDR3 RAM. Now, when I started making this PCB, I thought that the hardest thing was going to be the PCIe interface. But before we get into the DDR3 RAM, let me get into a little bit of background about high-speed signals in PCB design. So if we look at the PCIe interface, you'll notice I have these kind of weird traces where they hug each other really close and then they break up once they actually get to their signal. These are differential pairs. Now, we've talked about these in the channel before, but we actually haven't seen them, and this is what they look like. So the differential pair is just a pair of traces that need to be a very specific width. The trace itself needs to be a specific width, and the distance between them needs to be a specific value in order to match an impedance that's needed for the interface. Now, I'll be honest, I don't fully understand impedance and like what's actually going on there, but I know that when you're doing anything high speed, differential pairs are the way to go. Now, you'll notice that some of these are just tightly wound to each other, but then other ones have these weird little loops in them. And if I go to the bottom layer, which is the blue one, you actually see that all these have a ton of little squiggles in them. But if the point is to keep the signals really close to each other, why did I add these squiggles? Because the signals also have to be length matched. Length matched meaning that this signal, the one that I highlighted, and this one, the physical length of the traces needs to be very, very close. In the PCIe standard, it needs to be within 0.127 millimeters, which is 5 mil. Now the reason why this trace has all these squiggles instead of this one is because I'm breaking out of the ball grid array underneath the FPGA, and it's a very signal dense area. So you gotta do some tricks in order to get these actually out of here. And one of those tricks is to use these little squiggles to actually length match, because if you look, this signal is starting out much higher than this one. I say much higher, it's literally a millimeter higher. But doing that, you just need to make sure that you actually get these things correct, because if you don't, then you introduce skew in your signal pair, which I don't fully understand. I just know that high-speed interfaces do not like skew. So you want to length match them. So with that out of the way, let's discuss the DDR3 SDRAM and why this was such a challenge for me and why I severely underestimated it. So I knew that there was going to be differential signals in this. In fact, this specific integrated circuit has 3 of them. There is a clock differential pair, and then there are 2 data strobes differential pairs. Now, the differential pairs aren't necessarily the thing that's difficult about this, except for the fact that they need to have insane length matching. Like, they need to be length matched within 0.0254 millimeters, or 1 mil, plus or minus 1 mil. That's how close you need to get these lengths matched, which is difficult when you're trying to match it to an FPGA. But not only that, these DDR3 SDRAMs are actually broken up into byte groups. So in a byte group, you have 8 data lines, and this is where your byte is actually sent or received. And then you have your 2 pins that are used for the differential pair for the data strobe pin. And finally, you have a data mask pin. So all of the pins in the byte group need to be length matched with each other to within 0.254 millimeters or 10 mils. And on top of that, they need to be routed on the same layer and have the same number of VS per signal. All these things combined, it's really challenging to actually implement this on a PCB. And the last difficult thing about this is that in order to fully implement this 16-bit DDR3 SDRAM, I need 49 pins, 49 GPIO pins on the FPGA to route out to this. Now, this isn't an issue in terms of specs because one of these banks, which I'm using bank 16 for this, has 50 pins. So I would actually have 1 pin left over. But it's very difficult to actually get every single pin out of a bank because it's in such a signal dense area. And on top of that, you add that the DDR3 PCB specifications are so strict, it's very challenging to actually make that happen. So what's the plan here? We're just going to delete this and pretend that it never happened? No, we're going to learn from it. Instead of using an X16 version, which is just the version with 2 byte groups so you can send or receive 16 bits of data at a time, we're going to use the X8 version. The X8 version is nice because we actually lower our signal count by 11 signals because we have 1 less byte group to route out. This will make it significantly easier to adhere to the strict DDR3 SDRAM PCB specifications. And it'll also be easier because routing out less signals from your FPGA just gives you more room for error. So what are the benefits of switching from the X16 version to the X8 version? Well, it's mainly smaller size. So the footprints between the X16 and the X8 are actually very, very similar. But the difference is that the bottom 3 rows of balls, so these balls down here, are actually non-existent in the X8 version. Though we'll still need to go back and actually remake this footprint and make the schematic symbol. But this shrinking in size does come at a cost. But since we're cutting the data line in half from 16 bits to 8 bits, we're actually cutting our bandwidth in half, which bandwidth is how much data that interface can send or receive in a second. But it's not all doom and gloom, because since we have to redo this, I might as well show you guys how I go from the data sheet, make the schematic symbol, make the footprint, and finally hook it up in the final circuit. Let's do that. Hi, I bet you're expecting a montage. Well, I was planning on putting one in, but honestly, after making the schematic symbol and then putting the DDR RAM on the board and connecting everything up, I had 6 hours of raw footage. I then took that 6 hours of raw footage, did a ton of cut and edits, and then I increased the speed by 6 times, and I still had 45 minutes of footage. And honestly, for this video, which I think should be about 15 to 20 minutes, adding in 45 minutes of a sped up montage of me drawing traces on a PCB, I just didn't feel like that would be very helpful. So I decided to exclude that montage from this video. Though, if you're looking for a video that shows you how to do PCB design, how to make a schematic, and then put components on a PCB and connect everything up, then I would highly encourage you to subscribe to the channel. Because later, I'll be making a tutorial where we'll make our own FPGA development board. In that tutorial, you'll learn how to plan your project out, how to draw the schematic, and how to make the PCB. So be on the lookout for that series, which I'll start working on once the mangoPi revision 3 is finished. But with that said, here are the final DDR RAM traces. Now, I'll be honest, I did not follow every single specification that I was talking about earlier in this video. And that's just because it's kind of out of my skill level. You'll notice that there's no squiggles in any of these traces. And I think that this will be okay because the specifications I was looking at were for running the RAM at about 800 megahertz. Now, the FPGA can't even get anywhere close to running at 800 megahertz. And realistically, I would be perfectly happy if the FPGA could operate the RAM at 100 megahertz. That would be just fine for any project that you would want to use with the board. If I could push 200, that would be awesome, but we're just shooting for 100. So we can be a bit more relaxed with the PCB design specifications since we're running the RAM at a much lower frequency than the specification is calling for. So with the DDR3 RAM done, we're actually done with the board. Now, there's a few things that we need to do before we send this off to be manufactured. The first thing is, if you look over here, we have this DRC errors. Now, DRC stands for Design Rule Check. Before I started making this PCB, I set up some design rules. Now what these are is I'll say for this net, which could be GPIO nets, or there's a default net, you'll say, I want every trace in this net to be 0.127 millimeters thick, or every via connected in this net needs to be this certain diameter, and the hole needs to be this certain diameter. And you set these up so that while you're building and making the PCB, you can, along the way, just check and make sure that you're not doing something that you shouldn't be, that you're not doing something that's not manufacturable. And this is especially helpful when you're making these high-speed differential pair traces, because as I said earlier, these things have to be a very specific distance from each other, and they need to be a specific width. So you can use design rule checks to make sure that you're meeting those specifications when you're drawing them. Once we're done and we've solved all of our DRC errors, we can go on and actually look at making the bill of materials. Now, EasyEDA has a bill of materials tool, which if we click on, will bring up every single component that's on this PCB. Now, the thing about this is that the people that made EasyEDA also have an online component store called LCSC. So they try to encourage you to use LCSC for your components. And I've used LCSC several times to get components and I've never had any issues. It's just that the supply is a bit more limited when you're going into more niche areas like in FPGA. They don't really have any FPGAs on LCSC. It's mainly your passive components like resistors, capacitors, inductors, whatever they are. And then a few standard connectors. It's a large selection. It's just they don't have these niche components. And the other thing about it is when you're having somebody assemble and make your PCB, you can have the option to have the assembler get all the components and source everything for you. But if you do that, they usually have like an approved vendor list, and it's mainly DigiKey and Mouser are their approved vendors. So if you give them a BOM with a bunch of LCSC components, then they have to go through and manually find all these different components, which will add to the cost. So I like to use this export PCB BOM tool just as a template. So I'll literally take everything from the right of quantity and then just remove all that. And then I will go out and find all these components on DigiKey and Mouser and then put the manufacturer part number and then supplier be DigiKey or Mouser and then just do that for everything. That way it doesn't matter who I take it to be assembled, they will support those vendors. And then once we've gone through and got our appropriate vendors on the BOM, then really after that we just need to figure out who we want to make the PCB and who we want to assemble the PCB. Now, for who's going to make the PCB, I'll be using JLC PCB. Now, they're also the people that are behind EasyEDA and LCSC that kind of have this, full system set up for designing PCBs, supplying with the components, and then making PCBs. It's a really cool product, and I've used them 4 times before this, and the PCBs have always been fantastic. And honestly, they are one of the cheapest PCB manufacturers in the industry from what I found. So I could not recommend them more. And then as for assembling this PCB, with the revision 2, I actually had a Chinese assembler make the PCB, but honestly, it required a lot of my input into the process. I have an email chain with them where I sent like over 100 emails just clarifying things, and they even sent the board to the wrong factory to be assembled. So it was a lot of effort on my part, but then I was also worried about putting in the incorrect address because I had to take the PCBs made by JLC PCB and then send them to this assembler in China, which they have very different addresses from people in the US, obviously. And yeah, I was pretty worried about it just getting lost into the void. Luckily it didn't. So for those reasons, I'm going to go with a US assembler for the revision 3. So off camera, I'm going to do all the design rule checking, updating the bill of materials, and finding a US assembler for this board. In the next video, I'm going to go over everything I did off camera, and then I'm going to order this board and make it a reality. I want to thank you so much for watching. I know it's been a while since I uploaded. Life has been crazy, and I've obviously been going a little bit crazy with this every waking moment. So thank you so much for watching. I'll see you in the next video.